Friends, welcome to the 17th lecture. In this lecture, we are going to talk about earthquake loads as applied to offshore structures and the analysis procedure under earthquake loads. This is the first part of the lecture. In the second part of the lecture, we will take up a specific case study which is applied on a tension leg platform and show you the procedure, how the analysis could be carried out and what could be the interpretation of results, or on the other hand consequences on compliant structures under these kind of special loads, which is earthquake loads. The moment we talk about earthquake loads, we understand that ground acceleration causes displacement and that is an indirect load on the system. On the other hand, it is interesting to note that earthquake forces or earthquakes do not cause any force on the system. In fact, they displace the system at the connection point and this displacement induces forces. Obviously, when the system is with high mass value, inertia forces caused by earthquake forces will be also relatively high. So, the main component which governs earthquake loads can be the ground acceleration, which we express as u double dot g, the ground acceleration is actually considered, in fact, I should say is idealized as 0 mean ergodic and Gaussian process. That is a basic assumption which we make to model these earthquake forces for dynamic analysis. So, that is the first stage we have. The second stage is any system which is subjected to earthquake loads can be analyzed in time domain using a step by step algorithm. Many researchers have supported this statement and they have implemented this in dynamic analysis. I will show you a couple of references later in this lecture. So, the third issue is to do an earthquake analysis, use as far as possible, I mean if available, if available, as far as possible the actual earthquake record. Now, here is the issue. As far as land based structures are concerned, earthquakes are measured in amplitude and duration by various means, by using accelerograms, and people have records and they have past histories. Whereas earthquakes occurs on seabed, there were no such measurements available in the literature. Therefore, no real record where earthquake occurred on seabed is available for in the form of past records for analysis. The fourth issue could be for autocorrelation of earthquake acceleration. It is said that it will be reasonably small. For a time separation, that is tau. Autocorrelation function is taken for two samples with the time interval of a specific defined interval, let us say tau, and for a time separation of about 20 to 50 seconds, it is stated that one can assume that the process is stationary. Therefore, one can also use spectral approach, so very commonly researchers have used the following spectrum. For analysis of offshore structures under earthquake loads, people have used what we call Kanai-Tajimi power spectrum. The Kanai-Tajimi power spectrum has a very interesting reference. Kanai K 1957, semi empirical formula for seismic characterization of ground. Bulletin of Earthquake Research, Institute, University of Tokyo, 35 308 to 325, Tajimi H 1960, a structural method for determining the maximum response of a structure during an earthquake. Proceedings of Second World Conference in Earthquake Engineering, Tokyo, and Q2 volume level. Interestingly, once the spectrum is known, spectrum of ground acceleration is known, drag, wave radiation, damping and inertia effects. Of the fluid structure interaction should be accounted. On the other hand, the basic idea is offshore structures must be analyzed under the combination of wave loads and seismic loads. That is a very important statement we have. So, while doing so, we make certain assumptions. One, we assume that the seabed movement which causes ground acceleration is horizontal. Second, it does not move the ocean appreciably. What does it mean is the second order forces that can be generated in waves because of seabed movement is neglected. That is, additional wave forces that generally occur due to seabed movement is neglected. Only wind generated wave forces are considered. The third assumption, if the structural member is slender, it does not produce waves of appreciable amplitude. By their motion. Hence, effect of radiation damping is neglected. So, under the basic assumptions, under the above basic assumptions, let us try to generate the earthquake forces. Let us try to draw a figure to understand how the displacement causes forces. Let us say this is my origin of reference, let us say reference grid, this is my seabed, I have a cylindrical body which bends. Let us say the initial displacement of this is u g. At any z from the height, at any z, we say the displacement cost is u. Therefore, one can say u total is actually ground displacement plus displacement caused by the load. So, let us now consider the motion of supporting column member of an offshore structure in isolation. Let us talk only about the supporting column member. So, let the seabed be displaced by u g from its mean position, which I call as the reference grid. As a result, the column member deflects so that its actual displacement from the axis is perfectly as u at any depth z measured from the seabed. Let us say any depth z measured from the seabed. Total displacement u total is ground displacement plus the displacement of the cylinder. K into u will be the term associated with stiffness of the cylinder. So, the column member. C into u dot will be the damping term. Hence, equation of motion is given by m u double dot t plus c u dot plus k u is f z of t, because z is varying along the height or water depth and t of course on the time frame. Equation 2 Now, in equation 2, u double dot total accounts for the total acceleration, which is caused by the earthquake and cylinder motion. F z of t is the usual Morrison force. For the moving structural member, based on the knowledge which we had in the last lecture, I can write f z of t as C m v dot minus u double dot t plus C a v dot plus C d root 8 by pi sigma r v minus u dot of t, equation number 3, where C m is pi d square by 4 into C m into rho, C a is rho into a, and the last term approximates the drag linearization as we discussed in the last lecture. R refers to relative velocity term between the structure and the fluid. So, R is actually v minus u dot of t. Sigma r is taken to be equal to sigma v as first approximation, because I want to know the standard deviation of the relative velocity term. To start with, I assume that the cylinder is in the mean position, and I say that this value is more or less equal to that of the velocity only, but not the relative velocity between the cylinder and the earthquake motion. So, now I rewrite the equation of motion. I should say m u double dot plus u double dot g, that is my mu total, plus C u dot plus K u should be equal to C m of v minus u double dot g plus u double dot plus C a v dot plus C d root 8 by pi sigma v of v minus u dot plus u dot g. Call this equation number 4. Again rearranging, m plus C m of u double dot plus C plus C d of 8 by pi sigma v u dot plus k into u is now equal to minus m C m u double dot g minus C d root 8 by pi sigma v u dot g plus sigma m plus sigma a v dot plus C d root 8 by pi sigma v v. Now, knowing u double dot g and v, given the coefficients C d, C m etc., the above equation can be solved. For displacement u. So, friends, in this lecture we are able to introduce the earthquake forces. We said that earthquake loads are not direct forces, they induce displacements to the support, and because of this there are additional indirect forces caused on the members. In the next lecture, we will take up an example of a compliant structure. Let us say a tension leg platform, apply earthquake forces under the presence of wave loads and see or study the effect of consequences of earthquake loads on offshore structures. So, we are entering into an interesting domain of understanding of behavior of compliant structures, because fixed structures do not represent much of the displacement effect on the system, whereas compliant structures we understand they always alleviate the encountered loads only based upon the relative displacement between the cylinder or the structural member and that of the wave velocity. So, when they remain compliant, when they are anchored to the seabed using mooring lines or tendons, the effect of the relative displacement plays a very important role in counteracting the earthquake forces, but they also cause some adverse effects on the structural response, which we will try to understand in detailed manner in the next lecture. Thank you.